Hello everyone, this is Dilleswara from Aeronautical department. So last few classes we are discussing on this automatic control of aircraft control system design and how that the autopilot control system and also how the glide slope control system also been designed. That also we discussed on last class. So if you see the previous video, there we discussed about this glide slope coupler control system design and the transfer function design and how that with respect to that glide angle changing, how the transfer function has been controlling that thing also. We have given some part of explanation in previous video, that is we made it as a glide slope coupler and automatic flare control of part 1 video. So to continue that, this part 2 video we are discussing now. So this part 2 video will see most of the things depend upon velocity related things and how the coupling glide slope coupling with respect to velocity has been changed and how the transfer function will be designed for these things also we will discuss now. So let's go into the topic. As we see from the continuation of previous thing, that is glide slope coupler part 1 thing. So part 1 thing we gave the discussion on the frequency response of that control system up to that change of angle related thing only. So now with respect to the velocity, how the things have been conducting also we will see now. So here you see the effect of velocity control have been given in the below figure. So the have been given in below figure. So here you see the things have been started like the design and the analysis of glide slope coupler may be need to be continued here. So the geometry associated with the glide slope problem has been shown in figure 1. So here you see the aircraft below the center line of glide slope. That means here the ground, and when it is approaching to that gliding angle, so that gliding angle at about 2.5 degrees in the degree, and that has been changing with respect to that alpha plus 2.5, and like that gradually it is been changing of that, so that the CG of an aircraft also, which has been had an angle with respect to that glide with respect to that reference line also we've been shown here. So here you see the aircraft below the center line of glide slope, the D is considered as a negative. So here this is the D. So this has been considered as negative because of one negative angle, and that angle is called it as gamma. And then the velocity vector below the horizon, that is aircraft descending position. So the component of u perpendicular to the glide slope center is j. That means the perpendicular component for this is call it as j component. So so the relation for that relation for that d dash has been given here, like that means what, this is u, and if you want to make this this is a adjacent angle. So if it is an adjacent angle and this is an opposite angle, so if this is an opposite angle, then what will be the sine component of that one? So this is u. So if it is u is been having an angle like this, so this will be the cos component and this will be the sine component. So here the d we need to note, so that the d has been given as a sine component of that u. So that is u sine gamma plus 2.5 degrees. So that has been given here. No, so that angle of here it is gamma plus 2.5. So that will be equal to that sine value of been that sine value have been calculated here. So that is around u by 57.3 into gamma plus 2.2.5 degrees has been shown here. So the gamma plus 2.5 is in a positive value. Therefore, the D is a positive. Then the D is initially was but initially it has been negative. So the D we can write it like almost it will be equal to u by 57.3 seconds into gamma plus 2.5. So on the other hand, the factor must be included here is that the glide slope receiver does not measure the perpendicular distance to that glide slope center line, but the angular error that has been resulting thereof. So the value of the angular error increases as the aircraft nears the station. That means the angle of approaching, that angular error is being it's been increasing as the aircraft near to the station. So see here, if it is near to the station, this angle is been increasing. So here some angle, and after that here also the angle has been changing. And if you write it like this, so this is where this is the way the angle has been changing from point to point. So the angular error has been increasing as approaching to the station, which means increasing the system gain as the range to the station. System gain as the range to the station is decreasing in this figure 2. So there the tan d, that means this tan tau. This is a tau only. So this tau angle we have calculated with d by r only. So for the small angle, the r in the radius, that r will be in degrees or radian. So the tau value has been given here, that is 57.3 d by r degrees. So that the through the equation, that means previous equation 2 and 3. So this is equation 2 and equation 3. See, the flight path angle can be related to the angular error of the aircraft from the glide slope center line, and the block diagram of the glide slope angular has been given here. So here you see again there is a summing amplifier, after that the coupler, and that aircraft autopilot transfer function, and then that relation, transfer function relation with respect to r by gamma by theta, and for tau also u by 57.3, the tau value also been given here, and that 57.3 by 3, that controlling agent also been given here. So ultimately the output will be what, that tau naught. So that means the glide angle with respect to that horizon is been the tau naught. So the tau naught will be the output thing for this system. So to control that one only, we have designed this autopilot control system, that block diagram only we have given here. So figure C here, this is 3 only. So show that the coupler contains a proportional plus integrated circuit, that is a proportional and integrated circuit, plus a lead compensator also been given here. So the zeros of that lead network is been selected, so that they cancel out the closed loop poles at s equal to 0.05. So here you see that the coupler transfer function is 10 SC into 1 plus 0.1 by s into s plus 0.5 by s plus 5. I mean the transfer function, how it has been designed for this coupler. So this coupler transfer function will be this one. So that for here the s, if you take it as 0.5 from the basic autopilot input, so the factor of 10 is being included to provide the steady state gain of 1 for the lead circuit. So that is the lead circuit is being given proportionate to that one, so that the ls by that delta s, so that means that one of S by delta S will be the transfer function for required to convert that delta input. That means that elevator input, elevator output from that aircraft to aircraft and autopilot of the system. So here the transfer function gamma and can be derived with the relation theta minus alpha dash. That will be like what here you see that gamma of s by theta of s that previously you see, no. So this is the gamma of s by theta of s only. So uh, uh, so this transfer function has been designed like the alpha of s by theta, that gamma is been given as theta minus alpha. So that alpha of s by delta e of s into delta e of s by theta of s, like we are making the total derivative of that one. So that will be equated to that 0.0276 s into s plus 36.7 by s plus 0.585. So that so for this total equation of theta of s by delta e of s will be like minus 1.2 into s plus 585 by s into s square plus 1.5 s plus 1.47. So after simplifying and substituting that alpha of s and this alpha of s values and theta of s values in this gamma of s by theta of s value, so we got a ultimate value is like 0.276 into s plus 485 4.85 minus into s minus 4.35 by s plus 0.535. It's like here only that alpha s by theta, in terms of this we will substitute here, and in terms of this we will substitute here, and that will be equated to this one, so that we will get this gamma of s by theta. So the transfer function for that gamma of s by theta of s, we got it. That means this one only. So that transfer function we have designated with equation 4. So here you see the equation 4 is the transfer function that will be the control system designers need to be in the simplified form, so that total gamma of s by theta of s we have made it as a 0.585 by s plus 0.585. So this is make it as a equation 5. Then it has been obtained by neglecting the terms of s in your numerator of previous equation. Although the root locus analysis of this equation 5 will gives you a good results, and the equation 4 used in the analysis for as follow. So for the closed loop shown in previous figure, so this will be that theta of s by theta of s by theta comma of s will be equal to, that means total that theta value will be 46.5 into s plus 0.05 by this function we are getting for this. So this is the transfer function shown in figure 3. That figure 3 you see here. Figure 3 you've seen here. So that 4 and 6, this equation 4 and 6 will be the forward transfer function of glide slope control system that can be obtained and is given by figure 4, that is the upcoming thing. So there the maximum velocity is been 280 feet per second. So the zero angle root locus for the glide slope system for previous figure has been given by following slide only. So for this, the root locus coupler has been, the sensitivity constant is the 10 degrees of theta com per degree of ET. So that 10 degree of theta common will be we have taken as a degree of ET only. So the range of and the range to the station R provides the variable gain. So does it? Here you see that total transfer function for that is a simplified block diagram for glide slope coupler having that ET transfer function. that is epsilon t. Sorry, not ET. This is epsilon t only. So that epsilon t transfer function for that has been carried out for here. So here that R provides the variable gain. So thus it can be seen that the dynamics of system changes as the aircraft approaches the station. That means this will gives you the dynamic changes of system. So the this will provide the this problem involved in design of a satisfactory glide slope coupler that has been results from two poles of the origin. So one from the coupler and another from the geometry. So with that, without the zero value, like without zero at s equal to 0.1 value. So the proportional plus integral network. If you consider the proportional and integral network, the poles at the origin would move in immediately into the right of plane. Even with the 0 at s equal to 0.1, the poles at minus 0.5 will not be cancelled by 0 of the compensator. So the system would at least be only marginally stable for the limited range of ROA. That means here, if the real values of S is, the real values means that poles values are poles and zeros are we have considered, no. So the zeros of zeros at S equal to 0.1 and the pole at 0.5 will not be cancelled by that zero of that compensator. So that means zeros of that compensator means that the values at the imaginary axis only. So that will be marginally stable for that limited ranges of R values. So here that root locus plot for that glide slope system for that angle s equal to 10 has been given here. So here the R value been fixed here as 1340 feet. From the 1340 feet, it is approaching that gliding thing. So the range of the station provides that variable gain for the glide slope control system. So the root locus will be used to determine the minimum range of stable operation. For this case, the magnitude condition of that point where the root locus crosses the imaginary axis will leads at k of 27. So which must be equal to 3600 SC by R. So therefore that SC will be equal to around 134 SC. So here the SC will be 10. That will gives you the minimum range of 1340 feet only. That means that R means range will be around 1340 feet. So from the computer simulation, if you use for making this, if you see previously the root locus plot has been we use that MATLAB program also, and here also we will see manually. If you draw this one, you can draw, or by using MATLAB program for this also. For the function we already know. For that function, what are the S values also we know. From there, if you make out one MATLAB program, so that also you can get the this root locus plot. So further verifying the validity of using that short period approximation for the root locus analysis. So if the velocity control is being assumed here. So here the root locus plot has been making as a closed loop around this region. For a range 1340 been given here. That means here the SC is 10 we have considered. So the time response function for that transfer function is being given here. So the time response function for that block diagram is being see here when that velocity is being changing from -1 to +1. So there is an initial disturbance is there. Then after that it has been, that the damping is there. After that it has been stable. So if there is a change in that alpha, so there also there will be a slight damper. After that it is been getting controlled. And if it is a theta, that means that theta change is there. So for that also initial disturbance, and after that it is it has been controlling. And for the gamma and tau also, the initial disturbances for that S equal to 10 values, the frequency response have been given here. So this frequency response is giving that the behavior of that controlling transfer function, and how the transfer function is being used for making that input control for that control system also we can see from here. So because the here the damping range is been changing from minus zero point 0.5 to plus zero point 0.5, and here you see 0 to minus 4 also it has been changed, and here also zero point 0.5 to minus zero point 0.5 to plus zero point 0.5 and minus 1 to 1. I mean, here the maximum range it is showing. From there only the vibrations or that damping vibrations have been involving. If we avoid that, I mean, if you give values beyond that thing, so then it will be problematic things to make it make that thing to be stable condition. Because you see, what is the use of autopilot system? The autopilot system is to make that unstable condition to stable condition, make that aircraft bring back to that stable condition. So here if you see, for giving a small input only, it is getting this much of damping. If the damping, if you don't avoid, then it will be on unstable condition only. But to avoid that, this autopilot is automatic. Autopilot is controlling that system to make that in make that in stable condition only. So the results of that simulation things, we having that DF, the complete longitudinal equations of motion plus the basic autopilot and the velocity control system have been shown here in previous figures 6 and this 7. So here the aircraft was placed initially at 1400 feet. That is mean we make it as that range 1340 feet. Range we made that root locus plot now. So if we are making it as around 1400 feet above the station, so that is 100 feet below that glide slope. So that straight and level in straight and level flight. So the glide slope coupler control system was engaged as aircraft will be passed through that glide slope central line only. As if you see in figure, the aircraft was settled onto that glide slope, while the still the 3 miles from that station only has been the around that 3 miles from the station. So it has been stable only. But after that, there is a slight overshoot that has been 0.15 degrees only, 0.15. So which will be very less than there will be a minimum deflection value plus or minus zero point 0.5 only. So that plus or minus zero point 0.5 for the pilot's glide slope indicator. That means that glide slope indicator will be there. No, that indicator will show you whether that range from minus zero point 0.5 to plus zero point 0.5, I mean minus zero point 0.5 to plus zero point 0.5, within that range, if it is that frequency response is stabling, so that pilot can easily control that. If that range is been changing, I mean the range is been changing from beyond that limit, so that aircraft cannot be bring back to that original system. See here that initial there is an input is there, so that the small damp was there. After that one it has been approaching that same straight line only. So here that the ground station distance is around 1,000 feet. So height is around 100 feet. So if that if from that 100 feet from the station, so the glide approaching angle is been changing from small angle, but the even for that glide angle also, it has been initially having that damping, but after that it is getting into that controlling, I mean getting into that stable condition due to this autopilot system only. So here the final phase of landing is been the transition from glide slope to that actual touchdown, because while approaching for landing is not, it has to glide for certain path, and after that touchdown it has to roll on the ground. So generally referred as that that is called flare. So when the glide slope to the actual touchdown, I mean the transition from that glide slope to the touchdown, that means maybe it is gliding like this, and after that it is touching here the touching, and it is going on. So that is called that transition is called as a flare position only. So the rest of this section, this will be deals with the analysis of design automatic flare control. So the flight test data has been shown. I mean, flight test data, if you see, so when pilot perform the flare from the approach glide to final touchdown, he generally decreases its rate of descent in an exponential manner. So thus it tending to make the aircraft fly in an exponential path during the flare only. So for the automatic flare control, the aircraft should be commanded to fly at exponential path from that initial stage of flare until it touched down. So I mean that even from this transition rate, so from the initiation to the touchdown, between this transition state, it has to be controlled with that exponential path thing. So that has been defined as that h equal to h naught into e power minus t by tau. So here that minus t by tau is been the T by tau will be the controlling agent for this height controlling. So here the geometry of path illustrated in figure 8. So here you see here, this is the transition state just now we said now. From this transition state, the flight path has been how it has been designed, like if tau is known. So here if tau is known, so what is tau here? So the tau will be the that angle. So the tau is known. uh, so for a t equal to 0 from the initial condition, the h naught will be tau into h naught. That means here you see h naught by tau into e power t by tau now. So here the h naught will be equal to t into h dot. So that is h dot means h dot naught will be the condition at t equal to 0. So here the H naught is the rate of descent of that initiation of the flame. That means our initial condition, that rate of descent, where the then for a 2i that 0 glide slope and velocity at there the velocity will be 280 feet per second. So the H naught is there the H naught will be 12.2 minus 12.2 feet per second. So the desired value of tau can be obtained by the distance of touchdown point from the glide slope transmitter. So if the distance is 1,000 feet, then it is assumed that the aircraft touches down in 4 constants. So that is what uh, the velocity constant. If you see r plus 1,000 will be equal to 280 into 4 tau. So here, but h naught will be 12.2 tau, and from the previous above figure, so the tan 2.5 will be equal to h naught by r. So that is equal to that 12.2 tau by r. So therefore, that r will be equal to 280 tau. And if you solve for the tau we will get around the 1.18. So if you see that the h naught will be equal to minus h by 1.1 from the previous equation. So 1 by 1.8 will be like minus 0.8 h. So that means that h naught will be equal to 12.2 by 0.8. So that will be 15.2. So the controlling equation for automatic flare control is that it should be like h tau that h tau will be that h naught will be start from minus point h. So that is from the height 80% of height it has to 0.8 h it has to that h naught minimum the height it has to maintain will be point zero point 0.8 times of height h only. So the block diagram of that autopilot for this for controlling the controlling agent of this will be automatic flare controlling block diagram autopilot control system has been given here. So here you see The outer loop simply that this is a outer loop that has been simply supplies the rate of descent command HR. So that is that means this is the HR only. This is outer thing. So 1 by tau will gives you that HR feedback only. And the transfer function for aircraft autopilot is same as used for glide slope analysis also. That means that coupler and autopilot transfer function is same for previous thing only. So that hs by theta s transfer function can be obtained from h dot s by theta s transfer function. So that that thing will be, if you see, remember this thing on the previous thing. So that is u by 57.3 into the gamma s by theta of s. So that will be equal to minus 7.7 into s plus 4.85 into s minus 4.35 by 57.3 into s plus 0.585. So we are getting the transfer function for this autopilot system has been taken from that previous controlling agent only. So for this, the root locus plot will be automatic player control root locus plot is been given here. So it has been almost reaching to that reaching to that imaginary value when s equal to 3 degree per feet. So here the coupler transfer function will be this one. If you see that the coupler is there, no, here. So for this coupler transfer function is this one. So if you see that 10 sc into 1 plus 0.1 by sc, previously it is s plus 0.585 like that has been there, no. So here it is will be like s plus 0.5 by s plus 5 and s plus 5.5 by s by s plus 55 like that it is going on. So I mean, which is same as the glide slope control system only. Plus that additional network also been involved in here. So that second lead network will be added to obtain a higher value of coupler sensitivity. So to prevent the aircraft from flying into runway too soon, like when the height proper height it is not approaching means there will be a before approach before touchdown approach also will be there. So the to controlling that open loop transfer function has been given here to control that open loop or transfer function also. So that has been see here. So so here it is been it is there, no, that open loop transfer function also that has been given here. So the root locus plot, that root locus plot, if you see this one, this root locus plot is showing that the automatic flight control system, that location of that complex poles are indicated for coupler sensitivity of 3 of 0 theta common. Sorry, this is a theta common only. So theta common per feet per centigrade. The error rate of there is an error in rate of descent. So the results in computer simulation are being shown in 11 and 12. After figure, if you see here the figure 11 and figure 12. So it is found that the command equations must be changed for h equal to 0.6 h for a satisfactory operation. An approximation of a previous figure that yields that natural frequency of 4.6 radian per second has been compared with 4.8 radian per second from the root locus analysis. Though the damping ratio is difficult to measure because of that oscillation is superimposed on first order response. So, but it is probably between 0.15 to 0.2. So that the damping ratio has been given as I mean the 3 degree for feet second values, that damping ratio has been given here. So if this is the touchdown limit, so before that that engaging that transition stays from this one for different alpha, theta, and gamma and epsilon h will be been given here. So this is the transition rate. So if it is the desired path will be smooth path, but actually we are getting this much of damping path only for that SC will be 3 degree for feet second. For I mean the for a velocity it has been 3 degrees. That 3 degrees range, it has been descending one by one. So here you see that root locus plot is been zero point 0.9, so that agreement is considered as excellent only. So in the figure, the actual path is compared to the desired flare path. That means, so see here that actual path and the desired flare path has been almost same only, and the rate of descent at touchdown is approximately 30 feet per second. So which does not include that ground effect, and that would be present for an actual landing, and thus reduce the rate of descent further. So this would be considered as an excellent landing for, by any pilot, because if you see this autopilot usage, if you make it in for this transition race from glide to touchdown, so the desired path and actual path have been almost similar between the desired path and actual path. How we got from that experimental thing and from the computer simulation by using that glide slope coupler only. I mean that transfer function only. If you see that results have been compared with each other, so that we got that thing. So that here the rate of descent at touchdown will be generally 30 feet per minute. It has to be maintained. So which will not include that the ground effect that would be present for an actual landing, and thus reduces the rate of descent further. That means ground effect will not be considered here. So if it is touching down the ground, so further that rate generally that rate of descent will be totally getting down, so that there will be a drastic change in that, I mean the drastic decrease in that rate of touchdown. So this will be the good landing approach for any aircraft by using this autopilot system. So this is like while landing the thing, if you see that instrument landing system, and that beacons are arranged on that ground also. I mean that airport also will gives you only that aircraft approach. I mean approach means while it is landing to that runway, it has to approach that certain limit only. If you beyond the if it goes beyond that limit, then there will be an disturbed landing only. To maintain that one, there will be a automatic control system need to be control that aircraft. Then only it will be make it in a stable condition only, so that this automatic flare control system and glide slope control system also been installed in that autopilot system. So this is all about glide slope coupler thing. So actually previously we discussed the part one will be given the, I mean part one will be gives you that angular thing only, that frequency response with respect to that glide angle, and how to approach that glide angle also been discussed in part one. So part two we have given that glide slope and automatic flare control, and the transition range transfer function also been discussed here. So this is all about glide slope coupler and automatic flare control system autopilot that is installed in aircraft. So for any further doubts and further clarification, you can refer this book also for your information. So this is all about this video. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.